students, in this lecture we are discussing the central forces, effective potential, radial oscillation and equations of motion. Now coming to the central forces, you can write F as equal to F of R. That means the force depends only on radial vector, depends on radial vector, and it's towards the center. That means the force acts along the line joining two centers of the either mass or charge particle. Now this central forces, those what are called central forces? Central forces are acting along the centers of along the right here line joining the centers of two bodies. Okay, this is gravitation, and if you are considering the charged particle, centers of the charged particle, you can write bodies or charged particle. Okay. Now these are called central forces, and any central forces can be written as function of R, and if f of R is positive, it gives us a repulsive force. While if f of R is negative, you have attractive force. Good examples are minus gm by r square r cap. This is for gravitation, and also this is gravitational force, and electrostatic force. We have the equation K q1 q2 by r square r cap. Now if any one of the charges is negative, the entire force becomes negative, and this becomes attractive force. And gravitational forces are always negative because they are always attractive in nature. Here this is mass of one body, this is mass of the another body. Q1 and Q2 are the charges, and R is the separation. Here K is equal to 1 by 4 pi epsilon naught. Epsilon naught, as you know, it's permittivity. Now properties of particle moving under central force. Now, this is an important area. Properties of particle moving under central forces. Starting with the trajectory of the body. We're talking about the trajectory It's a plane curve. Plane curve, that means it can be represented in plane polar coordinates. Or two-dimensional coordinate system. These are either xy coordinate system or r theta coordinate system. So this trajectory can be traced in this way. So this is the distance r. This is theta. Now kinetic energy T is equal to half m r square theta dot square plus, so here we have r square theta dot square plus r dot square. So this is how you can represent kinetic energy. And potential V, as we know, it is a function of r alone. So the Lagrangian can be written as Lagrangian is equal to T minus V, that is half m, let's write r dot square first, r dot square plus r square theta dot square minus V of r. So it's the Lagrangian of the particle moving in central forces. Now coming to the second property, that is angular momentum. That is, let us write the second property is conservation of angular momentum. So in central forces, angular momentum is conserved. Now let's understand from the Lagrangian point of view. L is equal to half m r dot square plus r square theta dot square minus V of r. Now understanding the generalized coordinates, what are the generalized coordinates here? R comma theta, and since theta is cyclic, it means that Lagrangian is Lagrangian L is independent of theta. Now from this we can write P theta, which is equal to dou L by dou theta, P theta dot, which is equal to dou L by dou theta, which is equal to 0 because Lagrangian is independent of theta. So which means P theta dot is equal to P theta equal to 0, which implies P theta equal to a constant. So P theta means the angular momentum along the theta, that means angular momentum. So angular momentum is conserved. So that's it. Now coming to the potential energy, the third property. We know that V is a function of R, and if V is a function of position alone, so if V is function of position along position only, then total energy is conserved. It should not be function of velocity, not a function of velocity. Okay. Now then once again coming back to the angular momentum, J is equal to mr square theta dot. This particular quantity is constant, so J equal to mr square theta dot, which is constant, and theta dot is nothing but J by mr square. Now this is because we know p theta is equal to dou L by dou theta dot, and dou L by dou theta dot is the angular momentum given by, so L, Lagrangian is L is equal to half m r dot square plus r square theta dot square minus v of r. So dou L by dou theta dot is nothing but m r square theta dot, so this can be written as the total angular momentum, the angular momentum J, or you can also write L, because we are not using L here because Lagrangian we have already used capital L. So the angular momentum J is equal to mr square theta dot, and from here we get theta dot, that means the angular velocity, which is equal to J divided by mr square. To the effective potential, we have effective potential. So coming to the effective potential, consider a particle m moving under the central force, and Lagrangian can be written as L is equal to half m r dot square plus r square theta dot square minus v of r. Now we have the prerequisite knowledge on the total angular momentum, which is equal to m r square theta dot, and theta dot is equal to J divided by m r squared. Now with respect to the r, the radial vector, we can write the equation of motion as d by dt of dou L by dou r dot minus dou L by dou r equal to 0. So this is equal to d by dt of m r dot minus dou L by dou r equal to 0, that is equal to m r double dot minus dou L by dou r equal to 0. Now what is dou L by dou r? Dou L by dou r is equal to m r theta dot square so dou L by dou r is equal to m r theta dot square minus dou v by dou r. So substituting this in this equation, so this is 2, so substituting 2 in 1, we have so m r double dot equal to dou L by dou R. And what is dou L by dou R? That is equal to m r theta dot square minus dou v by dou R. Now from here we have theta dot equal to j by mr square, and theta dot square will be equal to j square by m square r power 4. So this gives us m r double dot is equal to m r, so here theta dot square, substituting this equation 3, let it be. So 3 in this equation, the last here we get j squared divided by m square r power 4 minus dou v by dou r. Now that is equal to, now writing it in this term, mr double dot equal to j square divided by mr cube minus dou v by dou r. Thus the force F of R is equal to mr double dot is equal to j square divided by mr cube minus dou v by dou r. Now since it is central forces, it is a conservative force, so it's a conservative force that are, so central forces are conservative, so because it is central force we can write F of R is equal to negative gradient of potential, so that's equal to dou V by dou R. So this can be written only if the force is conservative, okay, due to conservative force. Alright, now thus you can write the above equation, this equation in the form of f of r is equal to minus dou by dou r of, so it's j square by 2mr square, j square by 2mr square plus v of r. So if you differentiate this, we are going to get j square by mr cube minus dou v by dou r. So here minus and minus gets cancels, so if you want you can write it again, that's equal to minus j square by 2m r cube into minus 2 minus dou v by dou r. So that's equal to 2 gets cancelled, minus and minus becomes positive, j square by 2m r cube minus dou v by dou r. So this is F of R. Now this is termed as effective potential. Now this whatever is in the bracket is the effective potential, V effective. So this can be written as minus dou by dou r of V effective. Now what is this effective potential? V effective is equal to original V, that is the initial potential, plus j square divided by 2m r square. For example, let us consider a hydrogen atom for circular motion. So F force is equal to minus ZE square by 4 pi epsilon naught r squared. Now this is F electric, and this F electric is balanced by the centripetal force Fc, which is equal to mv square by r, and V effective is equal to V of r plus L square by 2m r squared. So now this L is nothing but the angular momentum. Earlier we have used the capital letter J to represent the angular momentum. Now to understand the stability of this with respect to the radius, we have V effective is equal to V of r plus L square divided by 2m r squared. Now since centripetal force is equal to the F electric, the net force, or F effective, the effective force, is equal to 0. Now which means dou by dou r, the partial derivative of V effective, will be equal to 0. Now will be equal to 0, and this particular point, so put it equal to 0 and find r equal to r naught for stable equilibrium point. Now here also, when you equate Fc equal to Fe, you get the value of r equal to r naught, the radius of the circular motion. Now here this r naught is the radius of circular orbit. Now so dou by dou r of V effective, now we have to bring this V effective from this to this partial derivative, which gives us dou V by dou r minus L square divided by mr cube equal to 0. Now when you put this value dou by dou r of V effective equal to 0, we get dou V by dou r minus L square by mr cube equal to 0, and from this equation we are going to find out the value of r such that F effective is 0. So at that point value of r, we write it as it is equal to r naught. So at r naught, F effective is 0. This is called radius of stable point. Here we have a question. Consider a particle of mass m mass m moving under the action of the central force. Now central force whose potential V of r potential V of r is equal to minus k by r. Then for what angular momentum? The orbit will be the circle of radius a. Circle of radius a. Now V of r is equal to minus k by r and L equal to, we don't know, we have to find it out. So V effective is equal to V of r plus L square by 2m r squared. So which gives us V of r is minus k by r plus L square divided by 2m r squared. Now we need the force dou by dou r of V effective is to be put it equal to 0, which gives us minus of k into 1 by r as minus 1 divided by r squared minus L square divided by 2m r square in r cube into minus 2 and that's equal to 1 by r square plus L square by mr cube equal to 0. Now this gives us this is k by r, so square r square gets cancelled. This is now we have we have, this is plus, so this is minus and k by r square, and this gives us L square equal to mkr. So L is equal to root of mkr. Now value of L at r equal to a, that is equal to root of mka. So this is the angular momentum when radius r is equal to. Here we have a very small topic, that's radial oscillation. The radial oscillation means we have a very rigid boundary or the radius here. Assume that the electron is revolving around this nucleus with some finite value of r. Now there is small force which is being exerted onto this electron, and the motion of electrons moves to be in some zigzag way. So this motion is known as the radial oscillation. This is caused due to small force exerted on the object which is revolving around something. Now the dou v by dou r, the total force is equal to 0, which gives some value of r equal to r naught. Now this value of r at r naught is called stable equilibrium point. Now dou square v by dou r square is nothing but checking whether it has some oscillation or not. So dou square v by dou r square at r equal to r naught gives k is equal to m omega square. So this value at r equal to r naught gives us k, which is equal to m omega square. From here we will get omega equal to under root k by m. Now omega is equal to under root 1 by m into dou square by dou r square of v effective. So dou square by dou r square of v effective with respect to r equal to r naught. Now when r equal to r naught, this particular quantity gives us the oscillation. That means this oscillation, how much it is there. Here we have another concept. We are understanding the dependence of angular frequency. Frequency omega on radius of circular orbit. Radius of circular orbit. So how the angular frequency omega depends on r, that is the radius, we can write capital R. Now let us suppose we know that the for central forces the potential V is equal to V of R. So that let us write this is equal to sum k times r to the power beta. Beta is some values, can be some whole numbers or integers. Yeah. So we write V of r is equal to k r power beta, and thus V effective potential is equal to V of r plus L square by 2 m r squared. Now that's equal to k r to the power beta plus L square divided by 2 m r square. Now the effective force V dash of, or V effective dash, that is the force effective, is equal to first derivative of V effective, that is equal to, with respect to this one, you will have beta k to the power, sorry, k r to the power beta minus 1 minus L square divided by m r cube. So this is what effective force. Now but we know that effective force is equal to 0. Now if the effective force is equal to 0, we can write beta times k r to the power beta minus 1 is equal to L square divided by m times r cube. Now from this we can write L square is equal to beta k r to the power, this is beta, beta plus 2, so beta plus 2. So now this is what we have, L square is equal to beta k r to the power beta plus 2. Now coming to the angular momentum, so this is equal to L square, let this be the equation 1. Now we know that the angular momentum L is equal to mvr, mass, velocity and the radius. Now velocity v is equal to again r omega, so we can write together this one, L is equal to m r square omega. This is just because we need to remove v and bring radius and omega, or we have to write it in terms of omega. So L we have, now here we have L square. Now let us see what is L square is equal to. That is equal to m square r to the power 4 omega squared is equal to, now let now let us bring that L square here. So now we have made a mistake here. This is L square is equal to this, m also should be here, m beta k r to the power beta plus 2. So m k beta, m k beta r to the power beta plus 2. So this is there, and we need omega squared, we need omega in terms of r. Now omega square is equal to m k beta r to the power beta plus 2 divided by m square r to the power 4. Now that's m k beta r to the power beta plus 2, m square r to the power 4. So m gets cancelled, so that becomes k beta by m, k beta by m. This is r to the power beta minus 2, r to the power beta minus 2. Now this is omega square. Now what is omega then? Omega will be equal to root of k beta by m r to the power beta minus 2 divided by 2. So beta minus 2 divided by 2. So this is omega. So omega is proportional to r to the power beta minus 2 divided by 2. So if you have a function v which is a function of r given by k r to the power beta, then the frequency of oscillation will be equal to or proportional to r to the power beta minus 2 by 2. For example, if beta value or v is equal to k r to the power 4, then beta minus 4 minus 2 divided, so omega will be proportional to 4 minus 2, that is 2, 2 by 2, 1. So omega is proportional to r. So this is the idea. Now we have omega is proportional to r to the power beta minus 2 by 2. Now omega can be written as 2 pi nu, which is equal to 2 pi by t, is proportional to r to the power beta minus 2 by 2. Now time period t, this is t is time period, so time period t is proportional to r to the power 2 minus beta by 2. So this is omega, and here we have time period, how omega and time period are proportional to the radius. stability of orbit. Now in this session we are going to discuss how the stability of orbit is depending on the power of r. That means how we have written v as equal to v of r, which is equal to k r to the power beta or something. Now this beta value, how beta value determines the stability. So this is what we are going to check here, and let's write down, that is the first derivative of v with respect to r is 0. That is, the force has to be equal to 0, and at this particular value of 0 we define r is equal to r naught. That means at r equal to r naught, the first derivative of the potential is equal to 0. That means the force is 0, and the second derivative, dou square v by dou r square, that is nothing but the wave vector k, which is given by m omega squared. Now we are assuming, let there be a function f of r, which is function of r to the power n, or let us write down proportional, and that is equal to c r to the power n, some constant into r to the power n. Now this is the force is equal to c r to the power n. Okay, so that's the force. Then v of r is nothing but integral minus integral c f of r dr, right? F of r dr, so that's equal to minus c r to the power n plus 1 divided by n plus 1. So this is the v of r, which is equal to minus c r to the power n plus 1 divided by n plus 1. This we can write it as, now this entire term, k r to the power n plus 1. Now what is k here? Then k is equal to minus c divided by n plus 1. So this is equal to k. Now if the function f of r, that means the force, is proportional to r to the power n, then we can understand that v of r, its potential, will be proportional to r to the power n plus 1. Now so v of r is equal to k r to the power n plus 1. Now let's write down this minus. Okay, so minus k r to the power n plus 1, that's equal to minus k r to the power n plus 1. So this makes sense. Now we need v effective, and what about v effective? V effective is minus k r to the power n plus 1 plus L square divided by 2mr squared. So this is the effective potential, the original potential, plus L square by 2mr square. Now we are equating the first derivative of V effective, that is the effective force, equal to 0, which gives us minus k n plus 1 r to the power n minus L square by mr cube is equal to 0. Now so that's, yeah, that's now from here we can write m square, okay, that's equal to r to the power n plus 3. So r to the power n plus 3 equal to minus l divided by mk n plus 1. Okay, so mk n plus 1, yeah. So r to the power n plus 3 is equal to minus l, okay, so it's minus l square divided by this much. Now taking the second derivative of this, dou square v by dou r square. So here the second derivative of the potential, we would get minus k times n plus 1 times n times r to the power n minus 1 minus, sorry, that becomes plus 3l square divided by m r to the power 4. So m r to the power 4. Now we have to check what is this value equal to. So once again writing that second derivative v double dash, that's equal to minus k n into n plus 1 into r to the power n minus 1 plus 3l square divided by m r to the power 4. Yeah, so let's write take 1 by r to the power 4 out. So this becomes minus k n into n plus 1. If you take 1 by r to the power 4, it becomes r to the power 3, sorry, n plus 3, n plus 3 plus 3l square divided by m. So that's there. Now we need to substitute for l square. Now we already know that r to the power, we need to substitute for r to the power n plus 3, that is equal to minus l square divided by m into k into n plus 1. So just substitute this value over here, that's equal to 1 divided by r power 4 minus k n into n plus 1, r to the power n plus 3 is minus, this becomes plus l square divided by m k n plus 1. Yeah, so plus 3l square divided by m. Now we have this n plus 1 and n plus 1 here, and m k, nothing else goes, so k goes here, so k and k. So 1 by r to the power 4 n times l square plus 3l square divided by m. So that gives us l square divided by m r power 4 into n plus 3. So this is the second derivative at the given radius r. So this is what is the radius we have found for the given potential for the orbit to be stable. Now we are going to find out whether we are getting the oscillations, what is the correct oscillation. So this has to be positive. Now we know that l square, which is always positive, l square because it is squared, n plus 3 has to be positive, right? So when does this quantity becomes negative? This quantity becomes negative when n is or n should not be equal to minus 3. When n equal to minus 3, v double dash becomes 0. Okay, so it becomes unstable. Okay, so it should not be minus 3. So now what happens when n is greater than minus 3? So n is greater than minus 3 means it's always stable. Okay, so it's stable because v double dash will be positive. V double dash positive. Now n less than minus 3, so this becomes unstable. Now why it is unstable? V double dash is negative. Now why should v double dash should be positive? Because we know that the frequency omega is equal to under root so omega is equal to 1 by m times v double dash. Now v double dash at r equal to r naught. Now v double dash, since omega is the frequency, it is always positive, and this root has to be always again positive. This cannot be negative because we cannot have imaginary frequency. So imaginary value of frequency not possible. That's why we have this, and that's why v double dash has to be positive because m cannot be negative. So if n is less than minus 3, it is unstable. So for any value of n, this has to be greater than minus 3. Please remember, it is with respect to the force. Now we have considered force F is equal to function of R, which is equal to CR to the power n, right? CR to the power n. Now this n has to be always greater than minus 3. If you are considering the potential V of R, which is equal to KR to the power beta, then it should be greater than minus 2. Coming to the last session, that is the equation of motion. Now we know Lagrangian is equal to, that is for equation of motion for central forces. Okay. R theta coordinates will describe any force or any motion in central force. So L is equal to half m r dot square plus r square theta dot square. So this is the kinetic energy minus V of r, the potential. Now according to the formula that we have already did, the F of r, the force, is equal to m r double dot is equal to j square by m r cube plus this is F effective. So this is F effective is equal to j square by m r cube plus F of r. This is the force. Now if we substitute u equal to 1 by r, or r is equal to 1 by u, we would get the equation of motion as d square u by d theta squared plus u equal to minus F of r times m r squared by j square. So this is the equation of motion. To understand this concept, let us do problem, that is the trajectory of particle moving in a central force r is equal to e to the power minus theta. So find the force law. Now find the force law implies that f of r is proportional to r to the power something beta. Now this is plus, so our aim is to find out what is beta. Now we know r is equal to e to the power minus theta, and let r is equal to 1 by u or u equal to 1 by r. So if u equal to 1 by r, so this becomes, substituting this r equal to e to the power theta, this becomes u is equal to r to the power minus 1, that's equal to e to the power theta. So that's u. Now according to the equation of motion, we have d square u by d theta squared plus u equal to minus f of r into mr squared by j squared. Now we know that u equal to e to the power theta. Now the second derivative of u with respect to theta, you will get the same e to the power theta plus u is again e to the power theta equal to minus f of r mr squared by j squared. Now that's equal to 2e to the power theta. Now e to the power theta we will write in terms of r, because here we have r, so that is equal to e to the power theta is u, so this becomes 1 by r, because u equal to 1 by r. So 2u, that is equal to 2 times 1 by r, that is 2 by r. So thus we can write 2 by r is equal to minus f of r mr squared by j squared. Now f of r, the function f of r is equal to, bring this j square here, j square 2j squared by mr cube with a minus sign. Now f of r is proportional to r to the power minus 3. So f of r is proportional to r to the power minus 3. So beta value is minus